Hello, my name is Ezine Uzo Okoro. I'm from MIT, and on behalf of my co-authors and I'm here to discuss the ground-based demonstration of a 1U CubeSat robotic assembly. Our motivation is really in space small satellite assembly. We do believe that with the closure of two key gaps, the first being the standardization of electromechanical CubeSat components and the compatibility of those components with robotic CubeSat assembly, we would be able to close the gap and usher in space small satellite assembly. So our goal is on-demand, on-orbit assembled CubeSats. And the overview of our project so far is to have orbit-agnostic lockers that deploy, again, these robotic assembled CubeSats on demand. And we are calling lockers a spacecraft, really. The lockers are a spacecraft that are the size of a mini fridge with propulsion capability. We intend that it will hold all our systems, which includes robot arms, sensors, propulsion modules, for a 1U to 3U sized CubeSats. We intend for the mission to have 4 key phases. We are currently in the first phase, which is the ground phase, where we're developing the functional electromechanical prototype. And we hope to move on to the ISS phase, which is the technology demonstration of a flight unit, which includes launching this spacecraft locker to the Japanese exposed experiment module, the exposed facility there at the ISS, and deploying from there. And next we intend to move to a free flyer phase, where we would develop a free-flying spacecraft that will have the robot arms and components to assemble and deploy our rapid response CubeSats. Our final phase is a constellation phase, where we anticipate the free flyer to autonomously assemble and deploy CubeSats on command. And so what you see here in the top left is the internal view of the spacecraft locker, which I will explain in detail in the next chart. And you see the ejection here on the right of the top left quadrant, where a CubeSat is ejected from the locker. There are many benefits, we believe, to such a mission, and this includes several CubeSat configurations that would help evolving space needs. We believe that the ability to select sensors and propulsion makes it flexible. We believe that the resiliency of using robot arms for CubeSat assembly without humans in the loop is a benefit, as well as the efficiency that we get from assembling CubeSats in hours on orbit versus building them here and waiting for a launch manifest, launching them, and then deploying them. So, as I mentioned, the spacecraft locker is about 12 inches by 24 by 36 inches, and it's a locker that has, shelves with components, and there are rails that hold 2 robot arms that then assemble the CubeSat and eject it through a spring ejection system, and then deploys it. We intend to use the Japanese experiment module exposed facility airlock, which is larger than this spacecraft locker. So on-orbit assembly versus human in the loop is something that we hope to rectify, because we believe that in the future we would be able to fill a locker on Earth with spacecraft parts, launch these lockers, and then these lockers would then assemble CubeSats on orbit and then deploy them. And on the right, you have what we do today, which is at least a minimum of a 24-month development cycle, with at least a 35-day minimum launch manifest per CubeSat before we eventually deploy the CubeSat in orbit. And there are a plethora of missions. We know that are robotic servicing and robotic assembly missions, and also missions that use custom robot arms. However, we find that we have yet to see a mission that uses low-cost robot arms, COTS robot arms, and standardized modularized components that focus on robotic assembly of CubeSats and have mass and volume savings per launch manifest. So our first ground phase includes 3 steps in our laboratory prototype approach. The first step is the feasibility of the commercial off-the-shelf robot arms in space. Can we just fly and buy robot arms? What sensors and arms can we use? Are there thermovac motors that we should consider for space qualification? And the second approach that we went through was developing these electromechanical CubeSat components for the lab prototype and trying to ensure what parts would be compatible for our robotic assembly, which ended up being fastened with magnets. The third approach was, again, implementing the demonstration with a functioning satellite and 2 robot arms, putting that together without a human in the loop. What you see here is our robot assembly block diagram where everything goes through the servo controller board, and we have a computer here that connects to the force torque sensor, and also the Raspberry Pi camera, and the servo controller feeds commands to and receives information from the 6 servos that we have, the 6 servo motors that we have, which are then passed to the computer. And we had a number of requirements, but select requirements for the arm include 6 degrees of freedom in a kinematic configuration. We used the brushless 3D DC motors. We also had a maximum mass of 2 kilograms with a 1U CubeSat so that the robot arms don't have to lift anything greater than 2 kilograms, and a 1 meter arm length maximum for the robot arms as well, so that we would not have to extend the length of the spacecraft locker. On the sensors, we have a number of specifications. One of that is a force torque sensor that is a 6-axis wrist force torque sensor that measures the wrench of the end effector. We also had link strain gauges on the 2 links of the manipulator that measure bending and twist strains for each of the links. And we also have, a motor current sensor that measures the motor current of each of the servo motors that is being controlled by the motor controller. So our low-cost robot arm is from Low & Soul, and it was purchased off of Amazon. It's got 6 degrees of freedom, as mentioned, 6 servo motors. We use a Lobot force torque sensor, and it has a motor controller. We programmed it using the standard inverse kinematics algorithm, and as mentioned, we used a Raspberry Pi and an Arduino motor controller board to help with precision and accuracy. Our mechanical structure design involved going through a number of designs and deciding on what fasteners to use. We ended up with magnets and 2 current best structural options. The first has this purple rail. You see 4 of them, 4 rails, and the robot snaps these rails into the base and the top structure, and after sliding in the modular boards. The second option has no rails and heavily relies on magnets to connect the boards to the base structure and the top structure, as well as to each other. For our modular components, we found that using standard prototype boards was suitable for the robotic assembly lab prototype. We customized it to include photodiode for duplex short-range optical communications that will carry high-speed signals. We used connector pads to connect the round contacts and optical parts to an external PCB. We had LED pads. We also made use of a controller board. And what you see here is the sequence of steps that show the robotic assembly in 7 minutes and 34 seconds. So the first robot on the right picks up a board and places it in the structure, and the second arm places another board, and the third, and the first arm does the same, and then they keep going until the entire CubeSat is assembled. So the results are obviously the demonstration of this robotic assembly of a CubeSat with no humans in the loop in 7 minutes and 34 seconds. We standardize prototype boards as electromechanical CubeSat components with magnets. And we do see that this has a potential for improving the lead time for CubeSat integration and assembly, not just on orbit, but here on the ground as well. We did notice a decline in our robot arm accuracy after 120 iterations, so we need better motors. And so our lessons learned first begin with a power consideration that require better stepper motors for our TVAC tests for the International Space Station demonstration. We also need better end effectors because we found that the accuracy diminished with time as well, and intend to look into surgical robots which have better precision. We also will conduct a future trade study on low-cost offerings, because the goal of this was low-cost robot arms, and as we look for reliable stepper motors and reliable arms moving forward, we may have to trade on cost. So our future work includes, again, investigating robot arms that are better suited for space, the space qualification of the entire system, which is the robot arms, the components, spacecraft locker, and a number of optimization analysis for assembled CubeSats. So the first is finding the optimal CubeSat power requirements, propulsion sizing that can enable maneuvers that we will anticipate, selecting sensors and payloads that are best suited for missions for the CubeSats, and also simulation of electrical or chemical thrusters for propellant efficiency. So in summary, the objectives of the 1U CubeSat robotic assembly prototype was to demonstrate that we could conduct a robotic assembly with no humans in the loop for a 1U CubeSat. We could optimize integration time for CubeSat assembly, which was 7 minutes and 34 seconds in our case. And we could assess several modular configurations for boards, several mechanical structures, and payloads and propulsion options. And our path to the ISS technology demonstration includes applying for funding. We need about $1 million for a space qualification of the system, and so we're working on that, and additional assessments, as I mentioned, on the efficiency of space robotics, so that we have resilient motors, and also the exploration of the new NanoRacks airlock that we recently learned about at the ISS, to see if it's a better system for us to consider versus the JEM EF airlock. Thank you for your time.